Okay, well, let's get started. Welcome to our June community meeting. This has kind of been a long time coming. We pushed this back to our hackathon. I'll keep my sort of intro here real quick. We have Brian Zhao with us from China, so it's almost midnight for him. And so he'll be going first, but our talks from the last meeting are on the Prevega IO YouTube channel. We had a Prevega Streams connector, Prevega performance under highly parallel streaming workloads and key value tables overview. So check those out, share those out. Of course, the talks from this meeting will go up on YouTube as well. And I'll share those out right after we're done here. Just a few quick community development points. Prevega's first hackathon was successful. Big thanks to Angel Hack and Dell Technologies for putting it on and funding it. And of course, big thanks to all the participants. We did see some new first-time contributions from hackathon participants, which was really cool to see. And congratulations to the winners: Speedy Good Freight, package tracking application, and COVID Save runner-up, a COVID-19 social analytics application. Was merged to Dependency, a Prevega Sync for Dependency server. It's slated to go out in a 1.6.0 release of Dependency. The connector can be found in the Dependency repository, and the docs are up on their master branch doc site. And just one maybe point of order, the 091 release is coming soon. So if you have them, get your PRs in order. I know I have a few PRs to dust off and get into the 091 release. So heads up to everyone else. And today's call will be hearing about stream processing for Apache Flink with Brian Zhao, video processing with GStreamer. Claudio will show us how cool that is, and then query processing with Presto, and I think Chip and Andy will be our presenters there. So I guess without any further ado, let me stop sharing, and Brian, if you want to get started.
Okay, so can everyone hear me and see the slides?
Yeah, looks good.
Okay, so let's go on. So, okay, I'm Brian Zhou from Dell EMC, and today I'll give an introduction to the Pravega Flink connector. So I'm now the maintainer of this repository, so I'll give the talk. So first, I'll give the introduction to both projects to see what is Prevega and what is Flink. I think most of the people here know what is Prevega, that we can just recap from the previous talks, and Prevega is a streaming storage, but not only stream, it also supports batch and key value tables and Bitestream APIs. And it also supports durability and consistency of the stored data. And it also offers high performance. With stream processing, you often want the low latency and high throughput of the data. And also it supports auto scaling and auto tiering features. And it also supports transaction support. I think people who really care about the correctness of the data, such as some financial use cases, are really focused on this support. So let's go to the Flink side. So it's very similar with the Prevega, but it is the streaming engine. It is a widely used real-time computing engine that provides unified batch and stream processing. So it's also not only stream, it also has stateful processing, and it also has the table API and also the batch support as well. So for rich use cases, it also has many of them, such as real-time ETL, and you can do some more analysis and monitoring. And you can also have the complex event processing and also graph processing even on Flink with some libraries supported. And with more, we can support machine learning and AI algorithms in real time. You can do the inference in real time and model training as well. And for performance side, they share the same philosophy that we should need low latency and high throughput. And it can run in a large scale and also support fault tolerance. So when the server is down, and it can bring it back quickly and still supports the exactly one semantics in the whole data pipeline and do not have any duplicates or data loss. So next, I will share more details on the Flink project. So I'll separate in two parts. The first is the open source part, and the other one are the production loads. So I'll take the recent news. Both happens on the year 2020. So on the open source side, there is a Apache Software Foundation project statistics, which is reported in 2020. It gathers the statistics of all the projects in Apache Software Foundation, which contains about hundreds of projects. And it ranked second by all the commits and also ranked second by all the visits, and second for most active and depth mailing list. I think these things can show the visibility of the Flink project, and the depth mailing list is the second most active, which also shows there are many developers who work hard on the Flink project. And to emphasize, Flink is the most active in the user mailing list. So we can see in the below ring graph, this is the whole percentage of all the user plus the depth mailing list. And we can see the bottom left, which is the largest, and to there it's more and more smaller. And we can see the first four. Three of them are coming from the Flink community. The first one is user, and second one is the simplified Chinese version of user, which use the Chinese language to ask and answer questions. And the fourth is the depth mailing list. So we can see Flink is a very active project on open source side. So on the other hand, we can see in production. I'll take the example of the Alibaba 11 activities in 2020. So November the 11th is in a shopping festival in China, such as just like the online Black Friday in Western countries. So at that day, maybe also starting from the November the 1st to that day, we are trying to buy all the things in the Alibaba group using the app. And internally in Alibaba, it uses Flink clusters to support many use cases, such as machine learning and advertisement and tracking and monitoring these stuff. So it supports many real use case in real production. And it actually gives back a very nice business result. So we can see the total gross merchandise volume is 74 billion US dollars. And on the back end, it has a very large Flink load. It has a 1.5 million cores of Flink clusters and supports 35,000 jobs. And at peak, such as, I think it is on November the 11th, 0 o'clock, there were many on-sale activities at that time. So people will click all the things at that moment. So we'll at peak have 4 billion records per second, 7 terabytes of data, which is a quite large amount. And Flink can handle them very well. So this also proves that in production, Flink is also a very good project. And it is also used in many other well-known companies such as Uber, Netflix, eBay, and some other more. So back to the combination, so with the help of Prevega and Flink, we actually can build a unified stream and processing model of, with the help of these two. So on the top of that, we can have the same model to treat historical and real-time data. And on the bottom side, we can store all the data in Prevega and have the same view. But there's still a missing part in the runtime part. So that's what the connector should do. It can feed the data from Prevega to Flink, and it can also sync the data out and persist the data into Prevega. And that's what the connector does. So next I'll show what is the connector. So I think both Prevega and Flink, as I just said, shares the same design philosophy that treats stream as a first-class citizen and also supports more like unified batch and stream. So I think they are the best companion of each other to construct a storage plus computing data pipelines. So we can see from this graph on the right side, we can see all the writes are in the real time to append at the end of the stream. But for read, we can have both tailing and catch-up reads, which can support both batch and streaming. And in below, it is the Flink abstraction. And we can see for batch, we can have data set, and for stream, we can have data stream API. And on top of that, we can have a unified SQL and table API support for that, which abstract two in one. And now Flink community is also doing a thing that it deprecates dataset API and trying to use the right side data stream API to support both bounded and unbounded dataset. So now Flink community is doing trying to abstract with one API to support both cases. And actually, Prevega Flink connector is doing much work with the whole development. So it now supports many features, such as parallel readers and writers, and exactly one semantics support with end-to-end. And it also integrates with Flink checkpoints and save points as well. And it also supports table and SQL API in both batch and streaming cases. So at last of this presentation, I'll demo about the table API usage and show how to query and doing processing with the table API. So next, I'll look back to the history of this project. So Pravega Flink connector is a project starting at the first year. I think it's also from the 2016. Well, that's also when the Prevega project is started. And at that time, the Flink connector is inside the Prevega repository. And in 2017, we have put all the connectors out of the Prevega repository. And that's also the start of the Flink connector repository. And at that time, it's still Flink 1.3, which is a very early stage of Flink. And now, today, Flink just released the 1.13 version. So it has been a very long time since then. And at that time, we integrated Flink checkpoint with Prevega checkpoint. So we'll have externally induced source support. And this is not like the basic APIs, such as the Kafka connector or POSA connector does now. So this is a cleaner way to support checkpoint. and it delegates all the checkpoints stuff all to the storage system, Prevega. Unlike the Kafka implementation, that Flink should care about what's to store all the offsets, committed offsets. So this is a cleaner innovation at that time, I think. So in the year 2018, we are more focused on the writer side. We worked with Flink community and implemented end-to-end exactly once. And both Prevega and Kafka are the first two supporters of this feature. And we are using the transactional writer. And also Flink does the two-phase commit algorithm, which helps to coordinate with the distributed consistency problem. So in the year of 19, we are fixing holes of the other things, such as we can now support batch read and writer. And we also added the table API. And we also forked out the branch to support multiple Flink versions and also have the watermark integration. And in these 2 years, starting from 2020, we are more integrating with new Flink features and also starting from integrating new Prevega features, such as the new table API from Flink and the Schema Registry from Prevega. So we are now doing the catalog integration now. So we talk about the high level things. So let's go into the detail of the code to see how to write a single job of Flink to use Flink as a processing engine to ingest and digest data from Prevega. So for the normal data stream API, we support two things: the reader for the source and the writer for the sync. So we are using a builder style API to support all these. And from the code level, we can see from here, we can start with starting an execution environment and define all the connection configurations to as a config. And we should define what is the event deserializer, how to deserialize from bytes to the actual either POJO class or your data structure. And then we can use the builder style API to construct the reader, which stream we read and using these things. And finally, we add the source to the data stream. And the sync side is quite similar. We can construct the Flink Prevega writer as well. And we can write the stream.addSync to write data into the Flink Prevega. So from the usage side, it's quite simple. And this one brings much simpler usage. I think it can also improve the user experience. That user can only write table API and write SQLs into Flink, and Flink can help dealing with all the computation and queries. So this is a create table clause. This is the connection of Prevega stream. So we can see, we can define the schema of all the data and also some connection details, such as the security, the controller, and the reader and the writer specifications. So next is how to import the connected dependency. I'll separate it in two parts. If you're writing a Java and Scala application, you'll basically package your application as a fast jar. So first you should choose carefully with your Flink major version, Scala version, and connector version, just as this XML shows. You should be careful with in the middle, 1.11, and Scala version 2.12. And this is the version which aligned with the Prevega version. So if you are running a Prevega server, which is 0.90, and we'll will suggest you using the same version of the connector. And with that, you can include this dependency in a shadow jar and package your application together, and you can have a shadow jar total, and you can upload to the Flink cluster and do all the computation. And you can refer to this one for further information for how to write in POM, XML, things like that, if you're using Maven. And second, if you are using Python or SQL application, so you should put the connector dependency in the Java class path. So this is a separate story. So we should first download the jar from Maven Central. Regarding all of our released version of connectors, you can download from Maven Central. And you should put the connector jar in the Flink Java class path, which is in this directory. And that time we can use direct Python support and SQL support for that. So next we'll plan for the future. There are many things we are currently doing, and we will also invite many of the more and more contributors, which can help us to do all the things. So first is the new API from Flink community. There are unified batch and stream source and sync API, which are the below two. They have a flip, and we're starting actively integrating with and also talk with the community. Second is the integration of Schema Registry. So we are building a Prevega catalog, which can abstract Prevega stream as a table of the whole table API. And now now in the master branch, we can support Avro format already. And we are starting supporting JSON, and in the future, maybe protobuf format. So next is the opportunities with integrating key value tables. We're trying to, this one is just in the POC part that we can write and read data from the key values. And with that, we can also have the absurd table support. For now, we can, the table can only accept append data, but with that support, we can enrich our SQL support. Okay, so these are the references that users can refer to write Flink applications when you want to read and write to or from Prevega. So this is the link of the GitHub, and this is the documents, which you can see all the details of how we implement and how to use the connector. And these are the samples repository, that contains all the Flink examples of that. And if you want to see more high-level things, you can see all the publications and presentations we are doing. In Flink Forward, we have many keynote speeches, and you can search on YouTube. So that is all of our the slides. So let's give a demo to further demonstrate the whole thing. So here in my local machine, I have started a Prevega standalone cluster. And also, the Prevega standalone cluster. And here, I also have a Flink standalone environment here, which is using 12.1 version. And I have 4 slots, and all of the jobs later will execute in a parallelism of 4. So first, I will start a data generation part. So this is the simple data generation stuff. I'm writing the JSON data into the Prevega stream. So we can see from the schema that it has 5 columns, 5 attributes, which this is the data actually from the retail use cases, which demonstrates how a user clicking, either it is clicking an item or it is buying an item. So you can see here, PV shows the page view, and the cart means it added the item into the cart, and this FAV is added into a favorite. And another behavior is the buy, which actually pay the money and buy this item. So this is the data, and it is now ingestion in a rate of 1,000 events per second. So this is the JSON data here we use. And today we will demonstrate how the table API can read the data and analyze the data. So this time I'll start a SQL client to demonstrate. Okay, so this is the Flink SQL client API. And first, we need to start the connection, how a Flink table is connected with a Prevega stream. So we should have a created table clause. We just, like I just showed in the demo, in the slides, we can write it as here. So besides these 5 attributes, we are adding a proc time, which is the current timestamp, and the watermark specification here. And below is how is the Prevega scope and stream abstractions specifications here. And with this, the connection has the bond. But it does not doing any read and write until I write this. This is a simple select star from user behavior from this table. So we can execute. And actually, when I wrote this to the Flink SQL, it will trigger a job in Flink cluster. So we can see from the Flink cluster, it is initializing this job, which it has the same name. Okay, let's wait a second. So it's now running. So we can see it passes the SQL into a job DAG. And we can see this is the DAG. And let's go back to the results. Maybe I can expand that. So we can see the 6 columns, including the current timestamp, is printed out here. It is showing all the events coming in, and the data is continuously updated. So this is showing all the data, which is quite simple. And the next one is a bit complex. So I will give a more complex SQL clause here. So this one is, I need some time to explain what this SQL clause means. So actually there's a cumulative user visit aggregation here. So this is the date. It's abstracting the date information, and this is abstracting writing the minute. You can see the hour and the minute, and it's substring with the first 4 characters and adding a 0 at the end. So it is having aggregations per 10 minutes. So it will start at 0, 0, which counts all the things in the first 10 minutes, and the next is the timestamp starting from 0, 10 minutes. And with this select, we can have an outer select. We can have this one is, I think we can use this one. So this is still the same, but this one, we can print out the count distinct user ID, which can count all the different users of these 10 minutes. So we can see how many users are clicking and visiting all the pages in these 10 minutes. So we can aggregate and do the deduplication and all the things in a single select clause. So if you're writing a program, it will be quite hard that you should handle all the windowing, such as you should window with 10 minutes, and you should also trying to deduplicate all the things. But with a SQL clause, it's quite simple. You can just use this, and I'll click enter. And this will actually upload the job to the Flink cluster. And Flink inside will pass the SQL clause into the action items and having a graph like this. So it will know that it will read from Prevega stream and adding a watermark assigner and aggregate with a group and window with and add windows and also deduplicate. And finally, it will print out to the console. So we can see the result updated here. So we can see that the first 10 minutes is now still updating. So we have 25,782 user clicks. And you can see the UV is updating, right? So in the 0:30, it is 15,722. And it also demonstrates how Flink handles late events, because when you calculate this window, maybe some late events from this window happens, and it will automatically update this UV user view in the result. So we can see here it is aggregating all the window results. Yeah, we can see the data is still moving ahead. It is now 143. So it is the up-to-date. It catches up with the stream and still doing the real-time processing with counting the user views. The value is still refreshing now. So this is the demo of the Flink table API for today. Okay, so that's all for today's presentation, and thanks all of you. And next is the Q&A. Anyone has some questions?
Hey, Brian, I have a question. In the SQL query that you showed us, how does that handle out of order events when you created that window?
So I'll show it here. So remember, I'm still sharing. So you can see this has a watermark specification here. with a 5-second delay, which means if the event time delays for 5 seconds, it is not ending the window processing. It is still updating the window results. Only the late events after the watermark, it is considered as the late events and maybe discard for the real processing.
So the watermark that you define with the table is used by the SQL query or by the select query below?
In the create table clause. So in the actual computing side, it's not using any watermark. You don't specify any watermark there. If it is not a late event, it will update the result just as shown in the result.
But the bottom query is a streaming query, right?
Yes.
Yes. So how does it know when to close the window for the time string? Like, is that 5 seconds after it receives a watermark? Well, 5 seconds after it receives a timestamp of the closing time?
Yes, of the closing time.
Okay, so the select statement uses the watermark defined in the table, in create table?
Yes.
Okay. Okay, thanks.
Hi, Brian. So whilst you're able to interactively query the stream, are you able to write the results out to another stream?
Yes, actually, we can do that. Like for now, we are using a select clause, but you can also add an insert into clause before that select. And you can insert into another table, for example, insert into the result table, select data string, blah, blah, blah. And first, you should create the result table. We can specify the sync. Maybe you want to write it in a JDBC, write into the database, and the connector should be JDBC. If you want to write to Prevega, it's also fine. You can specify the sync stream and use the stream. And if you create a table and finally you execute with insert into select, then it will start a pipeline, which finally it will pass the sync. It's not the SQL client sync. It would be your specified custom sync. It can be anything Flink can support.
Okay,
with
thanks.
a Flink SQL connector.
Do we have any more questions for Brian? That was a really great presentation, Brian. Thanks for doing that.
Yeah, thanks, Derek.
Up next is Claudio with video processing in GStreamer.
Okay, thank you. Let me start sharing my screen. Okay, hold on, wrong screen. Okay, are you guys seeing the big slide?
Yeah, that's good.
Video. Okay. Okay, so welcome. Thanks everyone for joining. My name is Claudio Fahey. I work with on the Dell team. So, and today I'm going to talk about how to do video processing in Prevega with GStreamer. I'll give an introduction to GStreamer in case you don't know what it is. I will tell you about the Prevega functionality that we have with GStreamer, including a Prevega Sync, a Prevega source, how to record video from a network camera into Prevega. And then I will talk about NVIDIA Deepstream Sdk for object detection. So that's a GPU accelerated object detection. And the Deepstream Sdk can be used for a wide variety of deep learning and AI tasks. And I'll talk about them at a high level. And then I'll show a quick demo of everything. And everything I'm going to talk about is of course part of the Prevega open source license. Okay, so GStreamer introduction. So what is GStreamer? So GStreamer calls itself a pipeline-based multimedia framework that links together a wide variety of media processing elements. So what does that really mean though? So I'll give you some examples. So the simplest example is GStreamer comes with a command line tool called GStreamer launch. And then you can give it a description of a pipeline, just write it out in text on the command line. And you can include various elements. So there's an element called V4L2 source. That's a video for Linux to source. So this is an element that runs on Linux, and it'll capture video from your camera. And then there's another element here called X264 encoder that'll compress the video, the raw video coming from your camera, into H264, also known as MPEG or MPEG-4. It's got many names, but it's basically compressed video. This exclamation mark you see them will link these two elements. So the output of your camera from video for Linux to source goes to the X264 encoder. And the output of the video encoder goes to another element called file sync, which writes to a file. And in this case, the name of the file is called myvideo.h264. So that's the name of the file, and it'll save that to my disk. And I can run that, and it just captures the video. The camera turns on, and it writes the file, and it'll run until I hit Control-C. So that's a very simple command line tool with GST launch. And I'll show you a few more advanced ones as well as ones that include Prevega. Okay, so GStreamer is a lot more than just this command line tool, although people usually start off with using it that way. I can build complete applications that use GStreamer as a library. I can write those applications using almost any language, Python, C, C++, Rust, Java, and more. You can build a video player, video server, DVR, a video management server, almost any application that's going to show video or audio or record it. It can be created with GStreamer. There are also 2,000 plugins available, or nearly 2,000 plugins available. So each of these elements here comes from a plugin. And on the GStreamer website, you can look and you'll see 2,000 plugins available to do various tasks, from connecting to various devices or doing some sort of video or audio processing. It has pretty much everything built in already, and it's pretty easy to make your own. You can write your own plugins in Python or C or Rust. You can't use Java for creating plugins, but you can use many other languages. If you guys have any questions, feel free to put them in the chat, and then I will look at them periodically. And I'll also ask for questions at the end of the presentation. Okay, so what can I do with GStreamer? Here is another example. I can play media from a video server, from a web server, a plain web server that serves files, and show it on the screen. So in this command, I use GST launch again. Playbin is the name of the element. That's a very powerful element. It just it will download the element, the file from a website, and then just figure out what it needs to play it. It figures out what kind of video compression, audio compression it uses, and it'll just play it on the screen. So here I can see I'm playing that, although it's on the slide, it's just a static image, but this will, if you ran this on your computer, it will play the short video. Okay, so what else can I do with it? I can continuously capture from a network camera and write to a fragmented MP4 file. So that's just a little bit more complicated. So a network camera is something that is connected to a network. Either it's a wired camera through Ethernet, or it could be a wireless network. And I connect to it using IP. And the IP-based protocol is that is common for network cameras is called RTSP, real-time streaming protocol. And that's based on several other protocols if you really want to get deep into it. But all you need to know for RTSP is the IP address. Sometimes you need to know that the path, and sometimes you'll need to know your username and password for your camera. So you'll type that here in the RTSP source location. Okay, another exclamation mark, because we're going to link it to the next element. Here I'm going to what's called a dpay. I'm going to depayload the H.264 stream from this. So RTSP can have audio and video, and it can have different types of compression algorithms in it. And this will tell it to pull out specifically the H.264 payload. And then I can send it to an H.264 parser, which does not decompress it. It simply it figures out where the H.264 frames start and end, and some attributes. And then that is sent to an MP4 MUX with a fragment duration. So this is actually what creates the MP4 MP4 fragmented file. Although it's not written to a file yet, it just creates the buffers that will be written to the file. So it puts it into that container format. And with a fragment duration of 100 means it's going to write a fragment of 100 milliseconds, and then end the fragment, and then it'll write the next fragment of 100 milliseconds. And then all this will get written to this file. And I can do something like play the MP4 file in something like VLC, and it'll detect it as a streaming file. And every 100 milliseconds, it will get a new fragment of that file, and then it'll play it. Okay, so that's there's a lot going under the hood in that, but it's fairly simple to write. I mean, it takes just 2 lines to write that. I can do something more complicated, such as transcode a media file. So transcode means I have a file in one format. I want to write a new file in a completely different format, but I have the same content. And in this case, I'm going to take it from this website again. I need to put things into a queue so I can run things concurrently on different threads. I'm going to use, there's an audio encoder and a video encoder. So the video encoder is called the Theora encoder. And then that's going into an OGG MUX, which is similar to MP4 MUX, but it's a different format. But the MUX will take the audio and the video, splice them together so that they can be written to a single file. So when you play back that single file, you have audio and video. And then the output of the MUX goes to the file sync. And then also in the same pipeline, we have the audio conversion part of that. So it looks, this is this pipeline has more than one direction. Well, it has more than one flow in it, which I'll show you graphically later. So it looks a little bit complicated written out in one line. So it'll make more sense in the next slide. Okay, so here's actually how the elements of the transcode are represented in GStreamer. So GStreamer takes that command line that I wrote, and it actually builds out all of these elements. I'm not going to go through each one, but I do want to highlight that it starts off here with just one element. So this is reading from the file. And then here it starts splitting up into audio and video. So it can process the audio and video separately. It'll decode the audio and then resample the audio, encode the audio, and then it gets merged together into a single file in the muxer. And the same thing happens with the video channel. It gets split and then it decodes, encodes, and then merges. And this is a little bit zoomed in. You can see the Theora encoder and the FLAC encoder, which is for audio. So the pipelines can be very sophisticated if you want. and wasn't all that hard to actually build that out. And GStreamer takes care of making sure that all the buffers are compatible. So the buffers are what are basically the data that flows from one element to another, and it has strong typing in there, so you can see that whenever data flows from one element to another, it knows exactly what it is. So this is raw audio. Here's the rate channels and even the type of format. And every single line between elements has a particular data type. So those data types help you build compatible pipelines. Okay, so what about Prevega with GStreamer? So I haven't talked about Prevega yet, so let's talk about that. So there are 2 plugins available for GStreamer that work with Prevega. So one of them is called Prevega Sync. It's a lot like the file sync, although a lot more powerful. So the Prevega Sync writes video or audio or both to a Prevega byte stream. It also writes a time index to an auxiliary byte stream. That time index is used for seeking quickly to a particular place in the video. So I can say I want to go to exactly 30 days ago and start playing from there. And it can seek to that very fast. It's also used for building a playlist if I want to use HTTP live streaming, which is a browser-based video technology. So basically, the index can give you a very a quick view into the entire stream that was written out, because at every keyframe it writes an index record, and I'll show you the details of that a little bit later. The Prevega Sync they can write any kind of buffer in GStreamer. It could be any format. What works well with some of our use cases is using either the MP4 container format, and specifically it's a fragmented MP4 container format, or an MPEG transport stream. They both work really well. Right now we're leaning toward MP4. It seems to work well for all of our use cases. The Prevega Sync will also write timestamps as 64-bit nanoseconds since 1970. And to avoid dealing with leap seconds, it stores everything using atomic time, which is same as UTC, but it doesn't go backwards when leap seconds occur. Okay, the Prevega source is basically the inverse of Prevega Sync. So it'll read from a Prevega stream and then output that to the rest of the GStreamer pipeline. Together, the Prevega Sync and the Prevega source have very low end-to-end tail read latency. So if a Prevega Sync writes a video frame, the Prevega source will read it usually within 20 milliseconds, which is going to be less than a frame. So it's going to be less than a frame away. Because it's a true stream in Prevega, there's really no difference in the API whether it's a historical read or a live read. It's just a read from Prevega from a particular offset. So writing an application that reads either historical or live is exactly the same, actually. You don't need to distinguish between them. The Prevega source has efficient seeks because it has a time index. Another thing that we can do with Prevega is truncate streams. So you may be writing a year of video data over time, and you want to then, you're filling up your disks, you need to make some room. So you want to delete the oldest data. So Prevega can handle that very well. You just specify the offset or the timestamp that you want to delete things at, and it'll delete all the video or audio before that time. So it deletes the oldest events, and it can be very precise. It'll delete it at any the keyframe offset. Okay, the Prevega Sync and source are written in the Rust language, and it uses the Prevega Rust client. but you can write your GStreamer applications in any language that GStreamer supports. So you can still write your application in Java or Python or C, and it'll just use the compiled Rust library for the GStreamer Prevega. And all of this is open source, Apache licensed, and available at the same GitHub site that has Prevega. Okay, so let me show you a little bit about the Pravega Bitestream format. So the Pravega Bitestream is a very flexible format. It allows applications to write pretty much any sequence of bytes to a Prevega stream. And there is no framing enforced by the Prevega client or the Prevega server. It's just a sequence of bytes. It's up to the application to make sense of that and write it out in a way that can be read reliably. So the GStreamer plugins have a specific format that they use so that this is reliable. So there's there's two streams, as I mentioned. There's the data stream, which is where the video and audio payload gets written to, and then there's the index stream. So the data stream is on top. And this represents two individual events written. So the first one is this the first four blue boxes. So everything it writes is written. It starts with an event length, and this is the number of bytes that the entire event is gonna contain. And then there's a few flags. For video, we have discontinuity and random access. So this is used by readers and decoders to know when they have to restart their decoding process. And then random access is used to know when there's a keyframe and you can start off a decoding at that particular frame. And then it's expandable to more flags as needed. Here we have the timestamp, which, as I mentioned, is nanoseconds since 1970. It's a 64-bit number, so it won't wrap until about 200 or something years from now. So it's storing this very high precision number is not really a problem. And the nanoseconds precision is what GStreamer uses internally. So that's why this is stored in Prevega. And that's high precision enough for even very high precision audio. A very high bit rate or a high sample rate audio. Okay, and so that's followed by a generic payload. And so this payload could be something like an MPEG transport stream packet, which is 188 bytes, or it could be a multiple of 188 bytes, or it could be an MP4 fragment, which may contain information for a single video frame or several audio samples. And it's for video, this could be a single keyframe or it could be a single delta frame. In fact, you can even make it so it's a keyframe plus multiple delta frames. The MP4 spec is very flexible, so you can pretty much make it. You can write whatever it is you want, whatever frequency you want to write it at, or whatever size you want to write it at. It'll do that. And this will be 0 to 8 megabytes. So if you want to write more than 8 megabytes, perhaps because if you have a keyframe larger than 8 megabytes, the Prevega Sync will simply fragment that, and you'll get multiple events. You'll get another event here with its own event length flags timestamp, and the payload, which is the remaining bytes. So you can write more than 8 megabytes. It handles that well. So this whole thing here is an atomic write, which is a primitive that Prevega supports, and it's extremely useful here because it means that either the Prevega Sync writes the whole thing or none of it, which means that when I'm reading it, I know that either the whole thing is there or none of it's there, so that there is no possibility of writing an event length without the entire payload following that. If that were possible, then they would lead to unrepairable corruption in the stream. So to prevent that, we have atomic writes, and that allows it to be that allows for no corruption. Yeah, even in scenarios where you have network outages that occur right in the middle of a write. Maybe I'm writing a 7 megabyte buffer and the power goes out halfway into that write. I'll be sure that I don't have half of a event written to Prevega. Okay, so the index stream it basically has 20 bytes per keyframe for video. We have flags. These are the same flags as what you have up there. Then you have a timestamp, which is the same timestamp as what you have in the data stream. And then you have a byte offset, which is a 64-bit integer, which is the number of bytes into the data stream that this event starts at. And then that just repeats every time there's a keyframe. It's about, and it's 20 bytes per frame. And it's, of course, it's ordered, so it allows for very efficient seeking. I can have a year's worth of data that's indexed, and you can just do a binary search to find the right timestamp that you need. Or I can do a scan of the entire index, and I can have a pretty good idea of the timestamps and the bit rate for the entire stream. And I can also do truncation at any point. I can just do a truncation right here at this boundary, or I can do a truncation at that boundary. As long as truncation occurs at an atomic right boundary, you also need to make sure that the truncation at the index stream is consistent with truncation at the data stream. But that works really well. And you can even truncate as you're writing more data, as you're recording more data from cameras to Prevega. Okay, so how do we do recording of video from network cameras into Prevega? So here's an example of recording from 2 different cameras. So we start off with a network camera, and then we have a GStreamer pipeline. So that's similar to the GStreamer pipelines that I showed you before, where you have the RTSP source right into Prevega. That's all this really is. You have an MP4 mux and a Prevega sync. And then it's writing to the video data stream and the video index stream. And then I have another camera writing to a different video data stream and a video index stream. So every single camera writes to its own stream that's dedicated to that. And this is still efficient because Prevega writes everything to segment containers. So it's not a problem at all to have thousands of video streams on a single Prevega cluster. It also allows for very efficient reading. So there's an application called Prevega Video Player, which will read video from a single stream and then play it on the screen, just as a standard, just as you would expect a video player to do. It's got a seek button, or a seek slider, so I can choose any point in time, and it'll take me to exactly that point and show me the video from that point. Okay, and I'll show you that in a demo in a little bit. Okay, so now I'm going to talk about NVIDIA Deepstream Sdk. Okay, so what is the NVIDIA Deepstream Sdk? So it's an analytics toolkit for AI-based multi-sensor processing. So and it supports video and image data. So it's built around GStreamer, and it has several GStreamer plugins. One of the plugins is a hardware or a GPU accelerated H.264 decoding and encoding and deep learning inference. They have a lot of other GPU accelerated plugins as well, or elements. But the most important ones that we're going to be using are these 3. So this requires an NVIDIA GPU, which could be a full PCI card GPU, a server class GPU, or it could be something like a Jetson Nano, which is a very tiny box that you can integrate into small robots or small applications. But it does require some sort of NVIDIA GPU. It won't run with just a CPU. Okay, so Prevega integrates with NVIDIA Deepstream with the Prevega protocol adapter. So the Prevega protocol adapter, it's an implementation of the Deepstream message broker. So one of the things you can do with Deepstream is object detection inference. So the output of object detection inference is basically for each image, it's going to be a bounding box saying, hey, here is a bounding box. Here's the X, Y, height, and width. And I believe that there is a car there. And I'm 0.5, I'm confident with a 0.5 probability that there is a car there. It might also do things like read the license plate number and output that with a certain probability. So that information is output using the Deepstream message broker interface. And that can be written to Prevega as JSON, for instance. So you can have a Prevega stream. In this case, this would be a Prevega event stream with that JSON data. I'll show you an example of that on the next slide. If you are using an existing Deepstream application that uses the message broker, you may be using that to write through some other message bus system, but you can just change one line in there, and it will use Prevega instead. The Prevega protocol adapter is not used for video or audio data. You use the Prevega Sync for that. The Prevega protocol adapter is also written in Rust, and it uses the Rust client. And this is also open source Apache licensed. Okay, so here's what it looks like to do real-time video object detection. So it starts out the same as the previous slide that I showed you, where we have a network camera, a camera recorder GStreamer pipeline, and that writes to Prevega stream. This first one is called camera 1. That's the name of the video stream. There's also an index stream, which I'm not showing just to simplify the diagram. Okay, now currently I'm running another GStreamer pipeline, which I call object detection GStreamer pipeline. It is accelerated with the NVIDIA GPU. So this object detection pipeline, first, it needs to decode the compressed video. That is GPU accelerated, and then it needs to run the deep learning algorithm to identify the objects. The output of that deep learning algorithm looks a lot like this JSON snippet. We have a camera ID to identify the camera. We have the timestamp of which corresponds exactly to the frame when it was captured by the camera. So that timestamp is maintained throughout from camera sensor all the way to object detection. So this is accurate to within hopefully nanoseconds. So this identified a vehicle. If you have the right AI modules, it will detect the type of vehicle, color, and the license plate number, and here's the confidence number of it, and here's the bounding box and coordinates of the screen. Okay, and so the JSON output of each of these two pipelines it can go to the same stream, which means I can then run a streaming analytics job using Flink, for instance, like what Brian just showed you. And now I can analyze the metadata from all my cameras using one Flink job. I can also use Spark, or you can use any analytics framework that Prevega supports. I can also configure the object detection pipeline to create a new video stream, which is just like the first video stream, but with the bounding boxes and the name of the object burned in, essentially. So it's basically drawing the red rectangles here into the image. And then I can view that again using the Prevega video player, because now it's just a standard stream. And the video player could play the original stream from the camera right here, or I can play this one here with the on-screen display with the rectangles. Okay, so here's a demo. I was going to show you in real time on a real system, but that's not going to work right now. So I'm just showing you a pre-recorded demo. what I'm doing for the demo is I have a camera recording. This was this is a camera on my desk, but it was a network camera, a wireless network camera. On the left window here is directly from the camera using VLC Media Player, using the RTSP protocol. That was getting recorded to a camera stream that was in the cloud, so in a different state across the country. And then I have a Prevega video player playing from that Prevega stream in the cloud. And this is before object detection. Then I have then I'm running object detection on GPUs in the cloud. That's being written to the on-screen display stream, and then that's being displayed in the Prevega video player here as well. So you will see a few seconds of latency from the left side to the right side. A lot of that latency is caused just by going across the country here. Some of the latency is caused by the GPU, and very, very little latency. I mean, just milliseconds is actually caused by Prevega itself. So I'll play this, and you can see what that's like. So it's detecting the car, and you can see on the right side it sees that there's a car. And as I move the car, you'll see that the bounding box also moves as well. And then the bounding box jumps around a little bit. Like on the free frames, there actually is no bounding box, which means that the orientation of it, it just prevents this very basic object detection from detecting that. So that's something that is just a limitation of this particular trained model. This is the pre-trained model that NVIDIA provides as part of their Deepstream Sdk, and it's a good starting point. But in a real application, you're going to want to retrain your model with your own data, just to get the best performance and reliability out of it. And of course, and also this model is only trained by is only trained to detect cars, people, signs, and bicycles. And in the real world, you'll want to test with more than that. Okay, so that's all I have to show for now. Hold on, well, that's all for the slides. If you guys have questions, go and ask them now. I also have I can show you a few things on the screen here for what you guys can do to start this up and run it on your own environment. But if you have questions, go ahead and start asking now, or just put it into the chat. Okay, so the first thing I'm going to show you here is, so I already downloaded the open source code from the repo. That's the GStreamer, the Prevega repo. So the first thing I'll do is start my own instance of Docker. So, sorry, not Docker, Prevega in Docker. This is different from the standalone installation because all the data is stored on disk, not in memory. The normal standalone Prevega stores everything in memory, which is great for simple testing, but for video, you'll run it in memory very quickly. So I use this script called up, and this will run everything in Docker. So I'll show you how that starts up. So right now it's stopping the previous installation. And this is a non-HA version. So it's only one instance of every type of container I need. Okay, so it's starting up. I don't need to look at all the logs. It is good. Okay, so I'm gonna go to the next window. And now I'm gonna run RTSP camera to Prevega Python. Okay, so this will connect to my RTSP camera and then record, basically record it to Prevega stream. Okay, So now it's running, and the only thing it shows on the screen is that it's every 2 seconds approximately, it's writing a new index record, because that's when it gets a keyframe from the camera. Okay, so now we're writing it to Prevega. Now I'm going to view the screen. I'm going to view the video on the screen using the Prevega video player. Oh, and one thing to mention is I ran the command and it ran very fast. The first time you do it, it might actually take you 20 minutes because it has to compile everything on your system. So if you didn't already compile it, give it about 20 minutes, and hopefully you have plenty of memory and CPU power to make that go faster. But the second time you run it, it'll be very fast, just like as what you saw. So here's the Prevega video player playing back the RTSP stream. Oh, look, someone's there. Okay. So and it starts off at the very beginning of the stream. But I can go to the very end of it, and now it's pretty much live right now. Let me get to the very end. I mean, it should be about maybe 1 second or less behind real time. And I mean, not much happens on this particular camera, but it. Yeah, but if I have 30 days of video, it would all be available here on this slider. And every single frame tells me the exact UTC time that the frame was captured. So that's going to be useful for very precise object detection. Okay, and then another thing I can do is the Prevega video server. So this here is a Linux native player. It can also be built for Windows and Mac without many changes. But it is native, so it won't run in a browser. A browser-based video player is served by Prevega Video Server, and here is what that looks like. So I just go to the URL served by that server, and I basically have the same thing here. But here I have the seek bar just like before, and I can play things. And this works in any browser, and it just needs port 80 or whatever your HTTP port. It just needs to pass through. The only drawback with this is that this uses HTTP live streaming, which is an Apple standard that works really well. But the latency is pretty high. So you might be about 5 seconds or 10 seconds behind live video. So it's not real good for watching live video. But if you want to watch historical video or anything older than 5 seconds, it works great for that. And it works across pretty much any browser, including mobile. So I think that's it for the demo. Are there any questions or anything else someone would like to see?
Yeah, I guess I had a question similar to maybe the Deepstream message broker that you wrote an adapter for. Like, there are some GStreamer elements that produce GStreamer messages on the bus as a part of their, like, for example, the level element. I can basically make VU meters, and it'll produce like a G object data structure per interval. Would I be able to tie in with the Prevega Sync and record those like decibel levels onto an alternative stream? Or
I believe so. The GStreamer Sync will write any buffer. So any buffer that it has, it will write it to Prevega. It'll put it into the payload section that I showed you.
mm-hmm.
Let's see. Let's see. Yeah. So, and the information that it records for every single buffer is just the timestamp and the number of bytes. If there's other metadata that your use case uses, that it may not be captured. Yeah, so like there is information in other information available in the buffer, such as duration. There's also the DTS, the decode timestamp. That information is not stored in Prevega because it's typically not, it's not used by the use cases that what we typically find. But if you need something basic like the PTS, which is the presentation timestamp, that's the main timestamp, then you should be able to store it and then decode it with the Prevega source.
Cool.
And it'll also index it for you in case you want to seek to a particular position. Okay, well, I think that's it then.
Yeah, that was great. I'm sure GStream is new to a lot of people, but that was really cool.
Yeah, thank you.
All right, I guess next up would be Chip with the query processing with Presto.
Okay, thank
Hey,
you.
Chip.
Thank you. Can you hear me?
Yeah, I can hear you pretty good.
Yeah, that was, I'm very intrigued by what Claudia was just showing. And this is a good lead into what we're going to cover here in this next presentation about with Presto. So video processing with Presto is a great use case. So let's get started. So let me share my screen. Let me start presentation mode right there. Alrighty, and share. 1 second. Let's go with that. Here we go. Alrighty. So this presentation is we're going to cover some work that I've been working on with some of my other engineers, the other engineers here at Dell. Flavio, you all know, myself, Andy Robertson, and we have some others, Karan, who's a new hire, and Raul is helping us specifically with the Prevega portion of what we're doing for this this project. And I did want to give a shout out to some interns that we brought on for the summer. They're helping us with this work, and it's some interesting work that we've been working on with analytics tool called Presto. So what is this presentation about? It is about something called Presto. I'm not sure if anybody's heard about it before. It's an open source distributed query engine. You're running interactive queries against large data sets from gigabytes to petabytes. Gives you that ability. There is some overlap with the concept of things like Flink, but I think Presto is a little bit different in a certain number of ways. We can talk about that as we move forward. I'm not a Flink expert personally, but you do have the ability to run these federated queries. Federated meaning data is going to be coming from a lot of different sources, and so that is the I think that's the separation here is in that not only can we execute queries against Prevega streams and key value tables, but we can also join that data with a whole lot of other sources, ranging from databases and NoSQL databases. We'll cover that in a second. So what is Presto? It is, as I said, it's this distributed query engine. It's not a database per se, in that it doesn't actually store the data or hold data, but it has the ability to query data in place or data where it lives, so you don't have to move data from one location to another. It's very scalable in that all you need to do is just add what they call worker nodes to scale the performance capabilities. We're looking at, and we've done a lot of work with getting Presto integrated with Kubernetes, and so we have operators that'll allow us to scale the Presto with Kubernetes and get number of workers to be changed very dynamically. We have, Presto has this concept of a coordinator who is the, basically, as you would expect, it takes the queries and does a lot of work up front. And what it does is it actually breaks the queries down as much as possible and turns them into, turns the workers loose on analyzing and retrieving the data, running through the queries, the SQL. I'm not a SQL expert. We've got a slide here that if you're a real SQL junkie, you can kind of really appreciate how the coordinator takes the queries and distributes and breaks it down. So it is an open source project, and it's actually, there are two camps. The first camp is something called PrestoDB. PrestoDB is the actual true open source project for Presto. PrestoDB is, we'll see later, is another slide, is run, managed by the Linux Foundation, but it does have the ability to, it is a true open source project. I already said that. Secondly, we have an organization called Trino, which is a enterprise version or enterprise supported distribution of Presto. You can get free, get Trino free, but it also has support in terms of you pay into the Trino licensing, and you can get additional support and additional capabilities. So we have originally sourced ourselves to the PrestoDB camp, and we are looking at the ability to also run on the Trino version. So we want to make sure that we want to see if we can run and support both versions of Presto. So a little bit more detail. Oops. Thank you. Why is Presto interesting? Well, it does run regular SQL, SQL, ANSI SQL, and it's very popular, and there are a lot of there's a lot of support for SQL. As I said before, there's a lot of data sources that you can attach Presto to. You can see the partial list on the side. You've got Spark, Hive is a very, very popular one. Hive is the is the database, the SQL-like database for Hadoop. Many customers run Hadoop. Many Dell customers, certainly with object data, they run that. But you can see the list and there's also a number of NoSQL databases as well, like Elasticsearch and MongoDB. So Presto calls these connectors. A connector, I think it was Brian, right, early on talked about the Prevega connector for Flink. And so it's a very common term here. And so Presto also calls them connectors. And so what we've done is we've added the ability, added a connector for Presto or for Prevega to read Prevega streams. We've talked about the scalability. The performance, things like performance are just bound by what you ask Presto to do, right? So if you're, if you scale very highly and you don't have the number of workers, you're gonna suffer the performance based on, based on what you've asked Presto to do. But again, the workers, many Presto shops have hundreds or thousands of workers, so typically they're scaled for that kind of performance. I mentioned who oversees Presto. It is run by a nonprofit group called the Presto Foundation. It's a governing. There's a governing board. You can see the organization of it. It's probably very typical for many governing boards that oversee open source kind of tech products. And the Linux Foundation is the governing, the auspices of the Linux Foundation. There's a lot of users of Presto. Facebook is where it originated from. I mentioned that earlier. They use it quite extensively. They have a large data warehouse, hundreds of petabytes that they use it for. Tens of thousands of queries, petabytes of storage, being searched every day. They do a lot of dashboard and test hypothesis of, whatever Facebook is, currently focused on, visualizations and so forth. So, that's Facebook is a huge user. A lot of batch stuff that runs by workflow management software, where they run things overnight and get the results and queries of the queries in the next day. And they're trying to get away from the legacy batch systems, and specifically Hadoop. And so a lot of the problems that Facebook was having was around Hadoop and the Hive queries that were taking just large amounts of time, and just they were not able to get queries done in a satisfactory amount of allotted time. If you're an AWS person, you've heard of Athena. Athena is essentially Presto underneath. There's a lot of obviously interaction and support for S3 data. They use a lot of Athena. AWS is for all the for clickstream. You can use it on for doing all your analytics on clicks and so forth. And an interesting thing here is that for schema management, and we'll talk a lot more about schema here in a few minutes, is done with AWS Glue, which is for that cataloging or schema management across all the services. And Athena has got huge and a lot of tight integration with all the AWS infrastructure. So we've got a lot of other customers who are people who use Presto, Airbnb, and so forth. So the team that I'm working with here at Dell, we have worked on a connector for Prevega, and you can find it on the Prevega GitHub repo. The location is right there. And so we've put up our first drop just recently, a month or so ago, and we'll be working on updating that. We're all kind of new. Some of us are new to this open source stuff, so we're trying to get into a good workflow here for managing how we update and how we add to the connector. There is a README, of course, and it describes how to do all the stuff with the connector to integrate it into your Presto if you want to try it out, and I hope you do. So a little bit more about Presto here. Presto has this concept of catalogs. Think of a catalog as just another source of data. So you would have a MySQL catalog, you would have Oracle catalog, if you're interested in getting, fetching data and joining it from Oracle. So catalog is the top of the hierarchy. Within that, Presto uses this concept or term called a schema. Unfortunately, that's a really overused term. I like to think of a schema as a database. So if you're familiar with Hive or Oracle, think of a Presto schema as a database, which is basically just a collection of tables. So you can see that from the hierarchy here, is that under a schema, you have a number of different tables that define a type of data or data input. Within each table, of course, you would then have columns. So you have to define how Presto is able to read your streaming data, how the columns are laid out, how the data is laid out in the data. Andy is our resident, Andy Robertson did a lot of the work for the Prevega stuff, the Prevega connector. But I think I understand. You have a lot of different ways that you could ingest data into a Prevega stream. And so based on how you've ingested it, you have to tell, there's a couple different ways to tell Presto how to read it. So Presto can read and understand the column and how the data is made up. But the columns are pretty much defined from the Presto point of view as your basic SQL data types, things like big int, varchar, and so forth. So you can see a sample number of rows of data here. You can just kind of picture what the various data types would be for the column definitions. So let's take a look at kind of how a picture of using Presto with Prevega, and also maybe another source of input like S3, and how you might stream that data or take the streaming data and other data and kind of combine it. So you start with your Prevega streams on one hand, and then you look at whatever kind of data you want to have coming in from other sources. And in this case here we, I'm using the term called things like bulk data, which is pretty much like object data. Whatever else you might have could be relational data if that's how you if that's what you're looking for. And then what you're going to do is you're going to query that data using Presto, and then turn it into a some kind of result. And I think I have another picture here up. So I was doing a lot of shuffling here of the slide. So here's the SQL breakdown of how the coordinator would take a sample query from a Presto user and turn it into what's standard SQL into some logical breakdown. So if you're a SQL junkie and you really like that, you can see how the SQL instructions on the upper left here, the select statement, the logical plan just turns it into joins, left or right joins, and then it actually then figures out how it can take that plan and distribute it across all the workers. We're going to talk a little bit about that and this concept called splits. And then once you have the distributed plan, it actually goes out and it gets run out on the cluster, and then it turns that into what you would call an optimized plan. The amount of processing that happens between the SQL and then the actual execution is pretty amazing. And again, this is something that we don't deal with. We let Presto do all the work. So let's take another example. It's kind of a different view of what we just showed, because I want to talk a little bit about taking the results, how the results can be processed. The user just creates the query, the cluster through the processing we just talked about, figures out which portions of the data, who's dealing with portion of the data. You've got Prevega input coming in from some locations. You've got other data coming in, for example, from an ECS bucket, objects from a bucket. This is showing them as CSVs, where portions of the cluster are reading that information. If there's joins to be made, that data is joined up, and then as the results are created, the results are generated or will be generated to either something like an ECS output or a Prevega stream, for example. So this is the workflow that we envision most customers obviously would be using something like a Prevega connector for Presto. How do you, if you decided to pull clone the repo off of the GitHub, there's obviously a README there, but some information about how to get it to talk to your Prevega. First of all, it's going to look the Presto is going to look for a Prevega properties file that defines your controller IP import, as well as the Schema Registry IP import. So you can see that that definition right here. So now, how do you define the big part of what you would be doing if you're going to pull in the connector is defining how to get the data from your stream. And so we have a couple different ways that you can do it. One way is that you can define some JSON, static JSON files that define your schema, put them out on the file system and point Presto to those JSON files, and it'll know how to where to go, which scope and stream to look for for the input data, and would be able to read it based on your definition. We also support the use of the Schema Registry to define how that data is laid out as well. So either you can use the JSON or you can use the Schema Registry, and we'll have a couple examples of that coming up here in a second. If you do decide to use JSON files, you would create them using a naming pattern. And a lot of this stuff may change over time as we're kind of finalizing how this code works. But right now, the way it's set up is that your JSON file would be created as scope.stream.json, so it knows where to, based on the name. It's also in the schema file itself. We'll see that. So as far as Presto is concerned, if you recall, the scope would be the schema. Remember that in the hierarchy, the schema is just under the catalog, which is kind of defined as a database, and then the stream would be kind of loosely associated as the table, as the Presto table. Soon you'll be able to use Presto itself to create table definitions. You'll be able to say create a new schema or create a new table, and you'll be able to define the table definition directly from Presto SQL. So that'll be coming down the road. Currently, the other two methods are what you got. So how does the JSON look? So something like if you wrote the Prevega stream using Avro records, you could, the events would be defined. First, you would define the JSON file accordingly. You can see it would, we have some COVID data in a demo that I want to show you here in a few minutes. But the scope would be the COVID data, the stream would be summary details, and then you can see in the event, it tells us that the format is an Avro format. And so we also would have then a Avro SC file, and you can see the schema definition for that particular table. So it's pretty straightforward. You just have to obviously have a good understanding of what your input data is looking like. If you wanted to do it using Schema Registry, this is kind of this would be kind of these instructions here. You'd have to define a group, a Schema Registry group, and you could, in this case here, we're listing the group. We can see COVID data summary details is actually the name of our group, but from the point of view of our actual schema itself, it may be a little hard to read, but if you've created schemas with Schema Registry, you know that the actual schema itself is base 64 encoded, so you can see that in the schema data definition. You can see the type here is a CSV, so we actually had pulled down some data that's in CSV format, so we basically just loaded the streams up with CSV data, and so we're indicating here accordingly. And you can see a different way to represent the schema here. If we decode the schema data that we just saw up here, you can see that it's pretty much the same thing. It's just the same records are part of that schema. Let's talk a little bit about performance, or how Presto will perform with Prevega. Presto has this concept called splits. Splits are used by Presto to distribute the workload across the workers. So it's up to the connector to try to break it up as much as possible for performance reasons. So we currently have one split is created for every stream segment that it finds. Andy explained this to me. You can use stream cuts to actually scale it out a little bit more. And basically using a stream cut, you can have more streams, more splits per stream segment, if I understand it correctly, using stream cuts. We're looking at using watermarks to actually also improve the ability to do more parallel reads. within the streams. And as we get down the road and do more work on this, we will be working on creating some more performance testing and verifying maximum performance that we can get out of this. So a little bit about the demo I'm going to show you. I think we should have just enough time to wrap it up by 1:30. As I said earlier, we have some interns that have come into our team for the summer. They're going to be using this code, and they're going to be creating some workflows as well as some other work that we have lined up for them. So this week we had rebuilt our Prevega cluster, and I leaned on the interns to get our data pulled into the Prevega streams. So it was a little bit of last minute processing and going on to create the schema, because it was new to them and it was new to me. Andy was out on paternity leave, so we had to kind of, it was a DIY kind of show. And the idea here is we have a good sized data set to start with this data. And we really just started today. I mean, as far as success in getting the data ingested. So I'm going to show you some of the abilities, but like I said, this literally just happened. This morning. When Andy got back, he kind of helped us figure out a lot of some of the things that we were doing wrong. So we've got some queries to run through, a very small subset of data. Hopefully, within a few weeks, we'll start to really build out the test data. We have some hardware-based clusters that we're going to be working on configuring. So that's it for the presentation. So what I want to do, or for the presentation, is I want to run through a handful of queries, and just to kind of show you the capabilities that we can do. And there we go. So what we have here is a 4-node Presto cluster. It's also sitting on top of the same 4 nodes that our Prevega is running on, as well as the Schema Registry. That's just how we've got it set up here. So what we do is we use a CLI, the Presto CLI, to talk to the Presto server, or the Presto coordinator, if you recall in the presentation. So we just indicate the IP and port for that particular server. And so now what we can do here is we can take a look at all the catalogs that we've got defined. And the catalogs, these are all SQL instructions. So we've got a Hive catalog, the Prevega catalog, a catalog for S3, and some system catalogs. Now I can use the system catalog to do information query about Presto. I don't want to do that because we're coming up on the top of the bottom of the hour here. But what I can do is I can ask Prevega or Presto to show us all the schemas that are defined for a particular catalog. And so you can see here we've got the Presto catalog, the Prevega catalog rather, and we have a couple tables. Some of them are trial and errors from our trying to get the data ingested. But we're going to use the instructions here that Presto provides us. Tell it to use a particular schema. So now we can say show tables, which is our basic SQL instruction. If I said it right. So summary details is the table that we're going to be working with here, and we can describe it. Yeah, hold on 1 second. All right, so here's your table definition. This is the data that we've pulled in from our repo, or the source of our Twitter data. This is essentially the first project we're going to be working on. Is just basically be able to do some some detailed analytics on this data, try to merge it and combine it with some other data sources to kind of refine it. We'll look to see at how we can present it and turn it into useful data. I know we've all seen a million Twitter or COVID-19 data points of interest, but we're creating our own here just for the purposes of this intern project that we have. So we can run things like we can find out how many tweets there are, or what if we can use a command like a select, and we can say find me all the what are the number of distinct languages that are in all these tweets, and this particular data set just happens to have just English data set tweets. You can look for the data, as you can see from the schema. You can ask for show me the number of likes that from the details. Show me how many. Is the quantity, or is that? I think that's just the quantity. Select. What if I said? Let me see. So if I said, I think that's just the quantity. Or that's just the yeah. It's just one row. So just one row has the data where the number of likes for that particular tweet is over 30. And then we can just get a total count, and you can see that the data set is not large. We've only got basically 100 records. So we haven't really pushed this yet because we just got this data set loaded up this week, today, in fact, Friday and yesterday. So you can see that using this Presto tool, the Prevega connector, we can easily write SQL statements. I can put these SQL statements in a SQL file and run them from the CLI. We have all the benefits that SQL provides for us. So that's it. We got 5 minutes to go. That's pretty much the presentation. If anybody has any questions, I think I'm ready to. I think that's it here. So I'll open it up to questions, and hopefully I can answer it. There. Now it's official.
I guess I have a question.
Sure.
Does the Presto connector store indexes, or will it, or does it always full table scan the stream? How does that work, or what's the future?
Yeah, there's no caching, right? It's not like it doesn't do a lot of the. I mean, as far as query optimization, like just hold on to a query because it might be used again. Is that kind of where you're going, Derek?
Yeah, or I guess my question was more about like indexes versus full table scan.
So, all right, so that we haven't, I don't think, I think right now, in terms of, what we're trying, and because this is relatively new, we haven't really worked on that kind of, any optimization yet. Just, within the past couple months, this year mostly, we've gotten this working effectively and for the Prevega side. And so I don't think so, unless maybe Flavio's got some thoughts on that, or Andy, but no, I think we're really, that's part of where we're, what we're trying to consider as we move forward is how to only read what needs to be read, essentially, right? And we're working on it.
Cool. Yeah. So that's future work. Sounds good.
Yep. Okay.
Any other questions? Don't be shy.
so you could see how, getting back to my initial comment, I'm very intrigued to see how we can use what Claudia was talking about with, because I'm very intrigued on using this for, analytics against video streams. I think that's a great use case.
So that might
Yeah,
be
that was only big. That'd be exciting. We should definitely try that.
so sort of using Presto to query against the bounding boxes or whatever.
Right. So picture one of the use cases we come up with is being able to we call it the smart garage, right? Or this or whatever you want to call it. Being able to take video streams, video data, and kind of reference that video metadata against some other external source, like a database of cars, right? So if you have, car information in a database and you're querying, like Claudio's demo here, where you take the stream and you see a car and you want to trigger anytime a particular type of car comes in with particular plates or whatever that gets read, so you can do some billing or something like that. Querying the metadata, you're finding certain plate information or car information, and based on the video stream, and then you can do a query based on that. So I think it's cool. I think there's a lot of cool stuff.
Yeah, I see. Like at a dealership service garage. Yeah, that's cool.
Yeah. And as far as futures work, if anybody goes to our GitHub repo, you can see the issues that are there. That's we're still working on it, but there's a lot of stuff coming up. So, but if anybody tries it, do a clone and build it and see if you can run against your data. Love to see that.
Yeah, that was awesome. Thank you, Chip, for presenting. Well, I guess we're pretty much wrapped up. It was really cool to see, Prevega's first connector, the Flink connector, alongside, Prevega's newest connectors, GStreamer Presto connectors. Well, I'll just wrap up inviting people to, find us and interact with us and join us in our community work. You can get a Slack invite at prevega-slack-invite.herokuapp.com. That'll get you access to prevega-io Slack workspace. And check out our blog, prevega.io/blog. It's updated occasionally. And you can find the next event at community.cncf.io/prevega-community. We don't have the next community meeting organized yet, but you can keep tabs on us there. Go sign up. We have a users mailing list at the CNCF at list.cncf.io/g/cncf-prevega-users. And you can follow us on Twitter at twitter.com/prevegaio. Thank you to the presenters. That was really informative, and I'm pretty excited about what we're doing. I'm sure others are. So thanks again, everyone. And with that, I guess we'll see you all next time.
Thanks, Derek.
Yeah,
Thanks, Derek.
Take care. Bye.